RF and high-frequency probes. For high-speed communication and wireless-related tests, signal integrity becomes the problem to solve. RF high-frequency probes use carefully controlled electrical and mechanical characteristics, often coaxial architectures, to support repeatable measurements and high bandwidth. This is especially valuable when the test setup must adapt to varied circuit topologies without forcing special pad geometries. Bead target probes and bead probing. Bead probing is a methodology that places test points directly on copper traces or top metal to form beads, which are then contacted by bead target probes during in-circuit testing. The value is test access. Beads can be placed where access is needed, which can reduce pressure to reroute signal paths just to create a traditional test pad. For low-force bead applications, designs that maintain strong internal contact at minimal force are favored because bead access is useful only if the electrical contact stays stable and repeatable. General-purpose probes and custom probes. General-purpose probes cover everyday board test, continuity checks, and standard production needs. When mechanical envelopes, pitches, or target geometries become unique, custom probes appear, built around the exact constraints of the fixture, the unit under test, and the expected life cycle. Replaceable versus non-replaceable architectures. In fixtures and adapters, replaceable probe strategies often use a mating receptacle permanently mounted in a retaining plate or block with retention features such as press ring knurl. This makes maintenance faster and reduces fixture downtime. By contrast, non-replaceable probes are selected when the probe is intended to live inside an end product or sealed assembly, where replacement is unrealistic or would risk damage. In rugged industrial use cases, designs that maintain stable performance under compression and withstand shock vibration are preferred. Solar panel probes. Solar panel testing is another distinct niche. Probes are used to create non-destructive electrical contact for reliable measurement, often requiring robust mechanics and consistent contact behavior on surfaces that can vary. How engineers choose the right probe. Probe selection is always application-driven. Mechanical parameters define the physical envelope and behavior. Overall length, working travel, spring force pitch, and alignment, tolerance compliance needs, and fixture constraints. Electrical parameters, drive materials, and surface engineering, current rating and contact resistance targets, plating choices, and wear behavior. Frequency, bandwidth, needs for RF integrity. Two recurring realities shape decisions. Harsh environments require shock, vibration, tolerance, and stable electrical performance. Time to market pushes rapid prototyping and quick iteration of fixtures, probe strategies, and contact geometries. Where Cotelec fits in France, Cotelec is presented as a market leader for test probes and test interfaces, with activity dating back more than 35 years. That long presence matters because probe and interconnect choices are never purely catalog decisions. They influence yield, stability, maintenance cadence, and the ability to keep production moving without being trapped in false failures and retest loops. In this Pacta Industry press review, the intention is to connect the vocabulary of probe families: step probes, switch probes, ICT, FCT probes, high current, high frequency, bead target probes, battery probes, and more, to the practical question every factory faces. What contact strategy protects quality and delivery with the least friction on the line?